Hi, I am Arib. You are watching my YouTube channel. Power factor. In electrical engineering, the power factor, PF, of an AC electrical power system is defined as the ratio of working power, measured in kilowatts, kW, absorbed by the load to the apparent power, measured in kilovolt amperes, kVA, flowing through the circuit. Power factor is a dimensionless number in the closed interval of 1 to 1. The ideal power factor is 1, also referred to as unity. This is when there is no reactive power through the circuit, and hence apparent power, kVA, is equal to real power, kW. A load with a power factor of 1 is the most efficient loading of the supply. That said, this is not realistic, and the power factor will in practice be less than 1. Various power factor correction techniques are used to help increase the power factor to this ideal state. To help explain this better, let's take a step back and talk about what power is. Power is the capacity to do work. In the electrical domain, electrical power is the amount of electrical energy that can be transferred to some other from heat, light, etc. per unit of time. Mathematically, power factor is the product of voltage drop across the element and current flowing through it. Considering first the DC circuit, having only DC voltage sources, the inductors and capacitors behave as short circuits and open circuit respectively in steady state. Hence, the entire circuit behaves as a resistive circuit, and the entire electrical power is dissipated in the form of heat. Here the voltage and current are in the same phase, and the total electrical power is given by. Now coming to the AC circuit, here both inductor and capacitor offer a certain amount of impedance given by. The inductor stores electrical energy in the form of magnetic energy, and the capacitor stores electrical energy in the form of electrostatic energy. Neither of them dissipates it. Further, there is a phase shift between voltage and current. Hence, when we consider the entire circuit consisting of a resistor, inductor and capacitor, there exists some phase difference between the source voltage and current. The cosine of this phase difference is called the electrical power factor. This factor, -1 less than cos theta less than 1, represents the fraction of the total power that is used to do the useful work. The other fraction of electrical power is stored in the form of magnetic energy or electrostatic energy in the inductor and capacitor respectively. This is called apparent power, and its unit is VA, voltamp, and denoted by S. A fraction of this total electrical power that does our useful work is called active power. We denote it as P. P is equal to active power is equal to total electrical power. Cos theta and its unit is watt. The other fraction of power is called reactive power. Reactive power does no useful work, but it is required for the active work to be done. We denote it with Q, and mathematically is given by Q is equal to reactive power is equal to total electrical power. Sin theta and its unit is VAR, voltamp reactive. This reactive power oscillates between source and load. To help understand this better, all these power are represented in the form of a triangle. Power factor improvement. Real power is given by P is equal to VI cos theta. The electrical current is inversely proportional to cos theta for transferring a given amount of power at a certain voltage. Hence, higher the PF, lower will be the current flowing. A small current flow requires a less cross-sectional area of conductors, and thus it saves conductors and money. From the above relation, we see having a poor power factor increases the current flowing in a conductor, and thus copper loss increases. A large voltage drop occurs in the alternator, electrical transformer and transmission and distribution lines, which gives very poor voltage regulation. The kVA rating of machines is also reduced by having a higher power factor as per the formula. kVA is equal to kW cos theta. Hence, the size and cost of the machine are also reduced. This is why the electrical power factor should be maintained close to unity. It is significantly cheaper. Difference between true power and apparent power. True power. The actual amount of power being used to drive the load or dissipated in a circuit is called true power, and it is measured in watts, symbolized by the capital letter P. Apparent power. The combination of reactive power and true power is called apparent power, and it is product of a circuit's voltage and current without reference to phase angle. Apparent power is measured in the unit of volt amps, VA, and is symbolized by the capital letter S. What is reactive power, kVAR? Reactive power is the unused power generated by reactive components, is an AC circuit or system, and is measured in kVAR. In terms of the power factor, the greater the reactive power is, the higher the apparent power of kVA is as well. In residential home, the amount of kWh used is quite low. That's why companies don't charge residential properties for it. The low amount of power doesn't cause any alarm for electricity companies. Commercial and industrial electric firms, though, consume this in massive amount, so electricity companies charge them a premium. Capacitor bank. Definition. When a combination of several capacitors are connected in series or parallel connection with the same rating, then it is called a capacitor bank. Generally, an individual capacitor is used to store electrical energy. So once capacitors are increased within a bank, then it will increase the energy capacity that is stored within a single device. In a substation, it is used to enhance the power factor and reactive power compensation. While installing a capacitor bank in a substation, some specification needs to consider. So capacitor bank specification is voltage rating, temperature rating, and kVAR rating and basic instruction range. Uses and benefits of capacitor banks. The primary purpose of a capacitor bank is to reduce the amount of electricity lost due to inductive reactance, which occurs when an alternating current, AC, passes through an inductor such as a transformer or motor. Connecting the capacitor bank across the line helps absorb part of the reactive power drawn by these loads, resulting in improved power factor and therefore better efficiency in your power system. By reducing the circulating current caused by inductive loads within a circuit, capacitor banks increase efficiency, decrease energy costs, and extend the lifespan of electrical systems and substations. Furthermore, capacitor banks are necessary for compensating reactive power in order to steady voltage fluctuations within a power system. As such, careful installation and management of capacitor banks is essential for optimizing the performance of both commercial and industrial power management systems. Causes of capacitor bank failures. Although capacitor banks are incredibly useful tools for improving efficiency and reducing losses, they can also fail if not properly maintained or installed correctly. Common causes of failure and unscheduled downtime include resonance between the capacitors and other components on the line, poor maintenance leading to overheating, unexpected load changes that cause excessive current flow, and harmonics caused by nonlinear loads like computers or LED lighting systems. All these issues need to be monitored regularly for your system to remain efficient and safe from damage caused by faulty capacitors. New technology developments in capacitor banks. New developments are being made all the time when it comes to capacitor bank technology and the way the devices are deployed within commercial and industrial power systems. For example, with controlled switching techniques now available, you can switch off particular sections within the bank without having to turn off the entire unit. This helps reduce wear and tear on individual components as well as lowering the energy costs associated with powering up a full bank again after every switch-off event. The same control strategies can also minimize the risk of inrush currents during energization, so that your system remains safe even when it's powered up again after long periods without use. Meanwhile, better subcycle control of the electrical current reduces the risk of voltage deviation and other disruptions, ultimately resulting in greater quality and predictability in newer capacitor bank devices. These new technologies give operators greater flexibility when dealing with difficult applications, making it easier to maintain electrical stability under a variety of different conditions. Capacitor bank connections. The capacitor bank is connected in two ways like star and delta, but most of the time, delta is used. So there is a bit of confusion about which connection is better for a bank. So here we are going to discuss these two connections along with benefits and drawbacks. The main application is power factor correction because, in a three-phase system, a three-phase capacitor bank is used for the power factor correction which may be connected in star or delta. Capacitor bank in delta connection. When these banks are used in delta connection, then is utilized for less to average. The capacitor bank in delta connection can be utilized for high voltage, however it is not achievable sometimes, as in delta connection, the complete phase voltage is given across every capacitor, while in star type connection, it is lesser as compared to applied phase voltage across the capacitor. So, three-phase capacitor bank. So if we employ a delta connection at high voltage, then the capacitor's voltage rating must be high. Consequently, manufacturing of high voltage capacitors is expensive and it is impossible sometimes. Advantages. The advantages of a capacitor bank in delta connection include the following. When the capacitor generates kVA reactive, kVAR, then that is proportional to the square of the voltage applied. So, if the voltage is higher, the kVAR is also more. So the capacitor in this connection will provide high kVAR compared to the bank connected in star connection, because, in star type connection, the applied voltage is low compared to delta connection. The capacitor bank in this connection can flow the harmonic current, thus it can decrease the effect of harmonic within an electrical system. When the bank is connected in delta connection, then it gives a balanced capacitance to every stage of the electrical system and keep a balanced voltage. If a capacitor cell within a single phase is not succeeding in the bank, then voltage beyond every phase remains the same, simply kVAR falls. Disadvantages. These disadvantages of a capacitor bank in delta connection include the following. The main drawback of the capacitor bank in delta connection is the pressure of voltage across every capacitor is maximum, which decreases the capacitor's life and it may not be utilized in the applications of high voltage. Capacitor bank in star connection. The star connection based type is mainly used in the applications of medium to high voltage. In this type connection, the voltage beyond every capacitor is smaller as compared to the voltage of the phase, so the pressure of voltage beyond the capacitors is less even in the applications of the maximum voltage. Advantages. The advantages of capacitor bank in star connection include the following. It is a simple connection. The voltage pressure across every capacitor is low, thus the capacitor's lifespan is high. Disadvantages. The disadvantages of capacitor bank in star connection include the following. Star-connected types provide less kVAR than delta-connected type because the voltage across the capacitor is less. A star-connected type cannot circulate the harmonic current in an electrical system. If a capacitor cell in one phase is failed, the unbalanced voltage occurs in the electrical system. Methods of power factor improvement. Capacitor banks. Synchronous condensers. Phase advancers. Capacitor banks. Improving power factor means reducing the phase difference between voltage and current. Since the majority of loads are of inductive nature, they require some amount of reactive power for them to function. A capacitor or bank of capacitors installed parallel to the load provides this reactive power. They act as a source of local reactive power, and this less reactive power flows through the line. Capacitor banks reduce the phase difference between the voltage and current. Synchronous condensers. Synchronous condensers are three-phase synchronous motors with no load attached to their shaft. The synchronous motor has the characteristic of operating under any power factor leading, lagging or unity depending upon the excitation. For inductive loads, a synchronous condenser is connected towards the load side is overexcited. Synchronous condensers make it behave like a capacitor. It draws the lagging current from the supply or supplies the reactive power. Phase advancers. This is an AC exciter mainly used to improve the power factor of an induction motor. They are mounted on the shaft of the motor and are connected to the rotor circuit of the motor. It improves the power factor by providing the exciting ampere turns to produce the required flux at the given slip frequency. Further, if ampere turns increase, it can be made to operate at the leading power factor. There are two main types of capacitor banks. Shunt capacitor banks. Shunt capacitor banks are connected in parallel with the load or at specific points in the system, such as substations or feeders. They provide leading reactive power, positive Q, to cancel out or reduce the lagging reactive power, negative Q, caused by inductive loads, such as motors, transformers, etc. This improves the power factor of the system and reduces line losses. Shunt capacitor banks have several advantages over other types of reactive power compensation devices, such as they are relatively simple, cheap, and easy to install and maintain. They can be switched on or off according to the load variation or system requirement. They can be divided into smaller units or steps to provide more flexibility and accuracy in reactive power control. They can improve voltage stability and quality at the load end by providing local reactive support. However, shunt capacitor banks also have some disadvantages or limitations, such as they may cause overvoltage or resonance problems if not properly designed or coordinated with other devices in the system. They may introduce harmonics or distortions into the system if not properly filtered or protected. They may not be effective for long transmission lines or distributed loads. Series capacitor banks. Series capacitor banks are placed in series with loads, lowering circuit impedance and providing negative reactive power to balance positive reactive power from capacitive components, thereby stabilizing voltage regulation. Series capacitor banks have some advantages over shunt capacitor banks, such as they can increase the power transfer capability and efficiency of long transmission lines by reducing line losses and voltage drop. They can reduce the short circuit current and fault level of the system by increasing the impedance of the fault path. They can improve the transient response and damping of the system by reducing the natural frequency and oscillations. However, Series capacitor banks also have some disadvantages or limitations, such as they may cause overvoltage or resonance problems if not properly designed or protected. For example, during a fault condition, the voltage across the capacitor may rise up to 15 times its rated value, which can damage the capacitor or other equipment in the system. They may introduce harmonics or distortions into the system if not properly filtered or compensated. They may not be effective for low voltage or distributed loads. How to calculate capacitor bank sizes? The size of a capacitor bank depends on several factors, such as the desired power factor improvement or reactive power compensation, the voltage level and frequency of the system, the type and location of the capacitor bank, shunt or series, the load characteristics and variation, the cost and availability of the capacitor units. The basic formula for calculating the size of a shunt capacitor bank is C is equal to QV2F, where C is the capacitance in farads, F. Q is the reactive power in vars, VAR. V is the voltage in volts, V. F is the frequency in hertz, Hertz. The basic formula for calculating the size of a series capacitor bank is C is equal to 1 to pi fx, where C is the capacitance in farads, F. F is the frequency in hertz, Hertz. X is the reactance in ohms, omega. However, these formulas are only approximate and do not account for other factors such as losses, harmonics, temperature, etc. Therefore, more detailed calculations and simulations are required to determine the optimal size and configuration of a capacitor bank for a specific application.